In the last class, we had started looking at interfaces by which embedded systems can be connected to the host. We were looking at USB interface. Today we shall look at USB IEEE 1394 as well as IRDA protocols for connecting devices to each other as well as to the host. So USB bus is basically a pooled bus. In fact, here all transfers are initiated by the host. The basic transaction steps are following. Host sends token packet, which actually tells the type of the data transaction that is supposed to take place as well as the direction. It also has the USB device number indicating the device for which the token is targeted, and also the endpoint number, which is a sub-device, because USB devices can be even compound device which may correspond to more than one device. Also, there is data transfer packets which flows on the bus as well as acknowledge packets. So basically, this is how the whole operation works. This is a USB host which initiates a token. This has got type of transaction, direction of transaction, and USB device address. So once that is received, depending on the type of transaction, the data transfer takes place, and the handshake packet is used for acknowledgement as well as completion for an transaction. The another aspect of the USB bus protocol is that of device identification. In the last class, we had talked about the concept of enumeration. So what happens is a device can get connected to a hub. Hub is nothing but something like a bridge in a USB system. So a device is connected to the port, and once it gets connected to the port, the indicator of the device flows via the port to the host. Now what does host do? It enables the port, allocate USB address to the device, and also it identifies the device driver which is required for the device. If the device is removed, the port actually gets disabled, okay, and the host removes the indicator, and host therefore can sense automatically whether the device is removed or not. So this USB organization we have also seen in the last class. So you have got these hubs to which the peripherals are connected. Okay, so it effectively increases the fan out of the network, and hubs are nothing but a bridge in a USB organization. So USB hubs are bridges which increase the logical and physical fan out of the network. A hub typically has a single upstream connection, and it can have many downstream connections. Hubs are themselves USB devices. The hubs, they detect the topology changes. We had already seen how this topology change is actually detected and propagated to the host, and the host manages the USB device addresses with conjunction with hub. They also are the source of power to the USB network, okay, because USB devices need not be separately powered if their power demand is not substantial. The USB communication takes place between the host and endpoints, and endpoints are actually located in the peripherals. In fact, each endpoint has got a unique address, and therefore if a peripheral consists of multiple devices, then each of the device would have a unique address, because each device will be mapped to an endpoint. In fact, these 4 bits define device's endpoint address. And the codes also indicate transfer direction and the transaction type, that is a token that which is circulated by the host, that indicate transfer direction as well as the transaction type. In fact, all transactions take place through pipes. Pipes are like virtual connectors, peripherals endpoints with the host. Why it's a virtual connector? Because the path can go through a hub, but logically there is only a single connection or a pipe between the device and that of the host. So when establishing communications with the peripheral, each endpoint returns what is called a descriptor. In fact, descriptor is a data structure that tells the host about the endpoint's configurations and expectations. Okay? So that guides the host to manage the transaction with the specific device that gets connected to the port. This includes, in fact, this data structure has got specification for transfer type. There are different types of data transfer which can take place on the USB bus. So it indicates the transfer type. It also indicates the maximum size of data packets, because that would depend upon the capability of the client device which is getting connected to the bus. Perhaps also the interval for data transfers, that means the rate at which the data transfer takes place, as well as the bandwidth needed. Why all these informations have to be provided by endpoint? Because it's not a pre-configured bus. When a device gets connected, the connection is established, and the host, by looking at the descriptor, would know really the capability of the device and the connection the device is looking for. That enables the host to manage the device. So what are the different kinds of data transfer which can take place on the USB bus? There are 4 types of transfer: control, isochronous, bulk, interrupt. These are the different types which are formally identified. Control obviously is that transfer modality by which the configuration information, setup and command information is exchanged between the host and the device. Bulk data transfer is that modality in which large amounts of data are moved, but these data really do not have time as a critical parameter. So their timely delivery is not really critical. So examples could be printers as well as scanners. So here we need to move large volume of data, but it's not necessary that this data has to be moved with certain deadline in mind. Okay. So in many cases, bulk transfers become fillers, claiming unused USB bandwidth when nothing more important is going on. Okay. Because since there is no deadline to satisfy, so it is not essential that the USB bus has to make a guaranteed bandwidth available to this transfer type. Okay. So it can be put in whenever there is a gap, but large volume of data is to be transferred. This is the basic aim. The interrupt transfers are not really associated with interrupting the CPU. Basically, the whole objective of the interrupt transfer is to transfer small amounts of data, small packets of data. So peripherals which are exchanging small amount of data that need immediate attention, such as mouse as well as keyboards, use interrupt transfers. In fact, this is a type of a transfer. You can say that this is a poled bus. Okay. The host initiates the transfer. So interrupt transfers are periodically initiated by the host to check whether these devices require immediate attention or not, and that is why they are called interrupt transfer. The last one is isochronous transfer. What is isochronous data transfer? Isochronous data transfer ensures that data flows at a preset rate, this is fixed rate, so that an application can handle it in a timed way. So, isochronous transfer is primarily targeted for time critical delivery of data. Okay. So, obviously, when we are streaming data from a audio or a video device, we are required to support isochronous transfer. Okay. So, what is important is that in this context, the USB bus has to provide guaranteed access. Okay. So, there has to be a guaranteed bandwidth allocated for this transfer. In this case, no error checking occurs, because whenever there is an error checking and if there is an error detected, there would be a requirement of retransmission. But retransmission obviously cannot be ensured if I have a really critical deadlines to meet when I am transferring the data. So, that is why with isochronous transfer, typically you do not have error checking, and system must tolerate occasional scramble bytes. If there are 1 or 2 bytes scrambled in a video frame which is being displayed, it might not really affect the quality of the picture, or even there can be software post processing to take care of this kind of scrambled bytes. In fact, this is a very basic principle which is we are discussing in the context of USB, but it is true for various other protocols which support isochronous transfers. Now, we shall look at another protocol which is IEEE 1394. This is again a serial protocol. So, it is targeted for basically high speed transfers, 400 Mbps and beyond, and in fact, this is what people are claiming as per the standard, which is 1394B standard. This is a serial bus. It has got the same plug and play capability. Just like in the USB bus, whenever you are connecting a device, the device is recognized. Here also the target is to provide plug and play capability. It also provides power. Okay. So, there is a power connection along with it. But in comparison to USB, the basic difference is here. USB is host based. That means there has to be a computer to which a client device is connected. But IEEE 1394 is a peer to peer protocol. Two devices can be connected directly. Okay. So, an embedded system is expected to support an USB interface when it is designed to communicate with a host. Okay. Typically, you will find say your PDAs or mobile phones, they come with a USB cradle by which you connect to the host, so that you can download software, utilities, your phone book, all these things onto your PDA or mobile from the computer. So, in such cases an USB interface is expected. This is also true for say a camera, okay, for loading the pictures. This is true for a digital recorder when you are loading a recorded music or a speech onto the computer. The other way around also, say an MP3 player with an USB interface can load the music which you have obtained over the internet on your host PC. On the other hand, if we are talking about connecting two such embedded devices without involving a host or a PC, I would like to enable IEEE 1394 connection on such embedded systems, because then two such peer device can communicate with each other. In fact, this FireWire IEEE 1394 is also known as FireWire. In fact, the original trade name, because this whole standard was pushed forward by Apple, they used the name FireWire. Later on, when industry accepted and went into an IEEE standard, it was termed IEEE 1394. It's a packet based structure. So, it is a serial bus, but it has got more like a packet switching network. Okay. So, that what you transfer is the packets. So, it is not really a circuit allocated dedicatedly for a transfer operation. It applications using disk drives, printers, scanners, cameras, there will be various of things which can be connected via this IEEE 1394, and it is capable of supporting a LAN similar to Ethernet, okay, but of a limited variety over a limited distance. It has got 64-bit address, okay. So, 10 bits for network IDs, you can have 1023 sub networks, 6 bits are for node IDs, and each sub network can have 63 nodes, okay. 48 bits for memory addresses, each node can have 281 terabytes of distinct locations. So, directly devices are in this way addressable, that is ports on the devices are directly addressable, okay. So, if you look into this, the whole application, this is a scenario which is likely to be realized through your IEEE 1394 connection, and all these are examples of your embedded systems, okay, other than possibly a computer which is a general purpose computing device. But if you see here, your stereo can be connected through IEEE 1394 to a set-top box, which gets connected to your DTV, digital TV. It can be a DVD movie player, it can be camcorder, it can be even a separate hard disk communicating with the computer via your IEEE 1394 connections. So, in fact, if you see, you can set up this kind of a complex network in your home environment or even in your office environment, and you can have maybe a movie which you are receiving on your digital TV, okay, which can be even put onto your hard disk if you have really this kind of a connection built. And this is really a peer-to-peer connection modality. So, let us see how such a network can be set up. This is an example where we have identified two work areas, work area 1 and work area 2, right. In work area 1, a video camera, a PC, a video recorder, all are interconnected. You have a digital video camera, you have got a printer, you have got digital video recorder, and this PC has got typically, let us say, 3 IEEE 1394 ports. So, they are connected, and what it says, the PC is also connected to a physically distant printer via 1394 repeater. Just like any repeater you use for conditioning of the signal, repeater extends the inter-device distance by redriving the 1394 signals. So, it is a repeater. And splitter is used to provide another port to attach a 1394 bus bridge. So, you have got this bus bridge by which you can connect other devices. Okay. So, this is another PC, another printer. So, this bus bridge, just like any other bridge in a network, isolates data traffic within each work area. Okay. In fact, we have seen that also for any of the bridges that we use in the bus architectures. So, what does that mean? That means I can have communication over this work area independent of the communication in the work area 2, but also at the same time I can communicate between the two work areas. So, bus bridges allow selected data to be passed from one bus segment to another. So, PC2 can now request image data from the video recorder in work area 1. Since the 1394 cable is powered, the signaling interface is always powered. Okay, I said that there will be power carrying. So, video data is transported even if the PC is powered off. Okay, although it is connected directly to the PC, the signaling interface which is expected to be powered, okay, on its own. So, it is not essential for this PC to work for the data to move from this digital video camera to this PC or the data to move from this PC to this printer for printing. Okay, so you have actually got a device to device connection independent of the host. Fine. So what is a protocol stack? So it has got a pretty complex, I should not say as complex as that of any networking layers, but it's a pretty sophisticated protocol stack. So at the lowest level you have got the physical interface, which provides the electrical, signal and mechanical interface, just like any bus structure we had discussed earlier. Then you have got the physical layer, which provides the encoding, decoding, arbitration and media interface, because the data, when it has to flow in and out, it has to be encoded and decoded appropriately. Then you have got a link layer, which controls the packet transmission and packet reception. This is a transaction layer which actually carries out the read-write transactions over the bus. And when it's an isochronous flow, we had already discussed isochronous flow, that is media data delivery, they are not strictly read-write transactions. So under that circumstances, you really need the transaction layer to come in play. There would be direct transfer, and that transfer is managed by the link layer, okay, and all these things through a serial bus management system. So physical layer provides what we call the initialization and arbitration services. So it assures that only one node at a time is sending data, right. Now the other aspects which this physical layer management module includes are electrical signaling, mechanical connectors, specification of mechanical connectors and cabling. See, this is very important for any of the standards, because otherwise you cannot have devices going into the ports manufactured by some other manufacturer. This is true even in the case of USB. Arbitration mechanism, then serial coding and decoding of data being transferred or received, as well as transfer speed detection, the speed at which really the device will respond and able to receive or send the data. The link layer's job is to extract and put data packets on and off the wire, okay. So it is actually constructing the data packets in that sense. It does error detection as well as correction, okay, because that's the basic necessity at that level, okay. So if I detect an error, I need to take appropriate action. One of the appropriate actions could be retransmission. It handles provision for cycle control for isochronous channel. We have already seen that when it's an isochronous channel, we really do not go through the transaction layer, okay. So it's a continuous flow of data. So you have to maintain the cycle, okay, by which the data is to be transferred, and that's what is handled by the link layer. Link layer also provides an acknowledged datagram to the transaction layer, okay. What is a datagram? Datagram is a one-way data transfer with a request confirmation, okay. So I can send a packet with a request confirmation, and that thing is detected obviously at the link layer, but the whole management of the datagram has to take place at the transaction layer, because that is keeping track of the data transfer and the nature of the data transfer that is taking place. So transaction layer implements what is called a request response protocol, okay. That means on the basis of the request, how the devices will send the data, and that request response protocol is the job of the transport layer. And the way it is designed, the basic specification is such that it minimizes the amount of circuitry required to interconnect with standard buses such as PCI bus, because one of the prime movers of these standards was PC manufacturers, and they would like the PCs to play a role, and it should not be just among the devices. So the standard is specified such that there is a compatibility with the PCI bus. And your host controller of IEEE 1394 is something like this, okay. Now let us try to understand what is what is specified here is that this is when we are talking about the system bus interface, these interfaces with respect to say system bus like PCI, okay, and this layer is IEEE 1394, and this is really the interfacing hardware, what we say that the physical as well as the link layers of 1394, and typically this is what is to be always powered up, because when I say that the host maybe a PC is not on, then also the data communication should take place, so that these signals should be powered on. And this interfacing is what is interesting and should be noted. These are all buffers, okay, and they are all buffers, so therefore they have to be organized as FIFO, first in first out kind of a structure. So this is for an isochronous transmit FIFO, this is asynchronous transmit FIFO, and this is an asynchronous response transmit. This is for the request, this is for response, okay, because it's a symmetric device, so it can request as well as it may be needed to send its response as well. Similarly, there is a receive FIFO, which is for the data which is coming from the bus. Now, these FIFOs will be obviously connected to what? If you are looking at a host interface, okay, they will be all connected to the various DMA channels, okay, they will be connected to various DMA channels, because this data has to be transferred now, because transferred to where? Transferred to the memory area, so that the processor which is sitting inside the embedded system can make use of this data. Okay. We have not looked at this interface for other buses. Other buses will also have conceptually similar interface architecture. Okay. So, here you find that for each one of them I have got indicated the DMA channel, fine, and what you have got? You have got the control registers. In fact, these control registers will essentially manage the overall DMA transfers. Okay. So, if it is really a DMA request, so that a processor should relinquish the bus and data get transferred, so that information will be generated from here, and what is the location where the data has to go, etc., all this information will come from control registers. Okay. Now, here obviously you will find that for different kinds of data, there has been different DMA channels which has been identified, okay, and here you find that inbound request handler is something which is different from other transmit handlers, okay. So, because they have to be configured, or these DMA channels have to be handled differently depending on the how the data is mapped onto the memory for subsequent usage. So, this interface is typically part of a PC. When PC is one of the IEEE 1394 device, it would be part of any other embedded system when that itself is participating in the IEEE 1394. So, typically you would expect similar kind of a controller, okay, with even your video camera, which is IEEE 1394 enabled. But but a video camera may not have an extended interface for receiving the data, okay, because it is supposed to transmit the data in response to a request, okay. So, there may be adaptations with the device specific characteristics, but all the devices would support this kind of a host controller architecture. In fact, this is a very basic feature to support all these interfacing protocols, although we are discussing only here in the context of IEEE 1394. Okay. And since all the devices that we are talking about, they are not passive devices, in the sense that it is not that they do not have a processor, they are all embedded devices having a processor, and that makes the fact that you can really have this kind of a sophisticated protocol implemented for this kind of interfacing tasks. Okay, if you just consider you would like to connect simply a dumb modem, okay, which is not doing anything, you cannot really do it in this way. Even if you have a USB modem will also have a small processor sitting inside or a control logic sitting inside implementing the whole interfacing logic. Next we shall look at wireless protocols. These are all wired, these two interfacing protocol that we have looked at, USB as well as IEEE 1394 are wired protocols. Now we shall look at wireless protocol. And in the wireless protocol, the most common, in fact very easily available today, is what is infrared protocol. I possibly should not say most common, because other protocols, that RF protocols, are also have become very commonplace today. So here you use infrared light for transmission of data, okay, which is the most distinctive feature of this protocol. So basic concept is very straightforward. You have got infrared diode which emits light to generate signal, and there would be infrared transistors which detect signal and conducts when exposed to infrared light, and that is how it actually detects the signal. This is a very simplistic conceptual scenario for implementation of this infrared protocol. It is cheap to build and obviously needs line of sight limited range, because if it is not in the line of sight, if your infrared transmission is blocked, then you cannot really have the communication. In fact, all of you use infrared control of your, say, TV, your sound systems, and this protocol is for doing data transfer over such infrared channel. So IRDA is a standard defined by the IRDA consortium, okay, Infrared Data Association. Now all these things have to be standard, simply because otherwise things are not interoperable. It specifies a way to wirelessly transfer data via infrared radiation. The specifications include standards for both the physical devices and the protocols they use to communicate with each other, okay. Because here the physical device specifications have to be with regard to the diodes and the transistors that are being used, and it can connect various mobile and embedded systems, and primary use has been to link notebooks or various what you call personal communicators, which may be PDA with cell phones and their variants thereof. What are the features of IRDA? So what we say that most IRDA work over distances up to 1 meter, and not very long distance, with BR, that is called bit error ratio between 10 to 9, and maximum level of surrounding illumination of 10 kilolux, because the surrounding illumination will have an effect in the detection of the signal. So that becomes a important point. So in fact, bit error ratio is the number of incorrectly transferred bits over number of correctly transferred bits, okay. In fact, it is 10 to 9 over 100 bits, okay. Now pulse modulation with 3/16 of the length of original duration of a bit is used, okay. Data format is same as for a serial port when it is asynchronously transmitting a word with start bit at the beginning. So this is how the pulse width looks like, okay. So what is really asynchronous transmission? If we look at an UART, we have seen that almost all the devices, all the microcontrollers, they have an UART interface. Typically UART supports asynchronous transmission, okay, and in an asynchronous transmission what happens? Typically clock is not part of the data. You have a start bit which indicates beginning of the data, and a stop bit which indicates end of the data. So, if we look at a simple example of RS-232C, okay, which is the most common asynchronous protocol, we say normally the signal lines are in what we call marking state. Marking state is typically high state for the signals, okay, and then when a data transmission is to start, that bit goes down, okay. So, typically you have got a start bit. So, this start bit indicates beginning of a data transmission, that is followed by the data bits, and then you have got a stop bit. These pulse widths are typically 3/16 of the bit time, okay. So, it is not that corresponding to the bit, okay, it will be always on, okay. So, what we are using is, it is effectively what? Effectively a pulse width modulated transmission. The pulse width is, so transmitter can use either 3/16 Mach to space ratio for one bit, or fixed length 1.63 microsecond of each optical pulse, which would typically correspond to 115 kilobits per second, and this is version 1. There are other versions where you can have faster transfers. Now, why pulse modulation? The basic requirement is that the receiver needs to distinguish between the surrounding illumination, noise, and received signal, okay. And therefore, if we have to have better detection capability, you would like to use the highest possible output power for the LEDs. Now, therefore, what we say that higher power implies higher current in the receiver, because as you get infrared, the transistor starts conducting, so you have a higher current flow, and that would imply better signal to noise ratio, okay. But IR LEDs cannot transmit at full power continuously over 100% of time, okay. So, a pulse width of only 3/16 of the total time for one bit is used. So, what it implies? It implies that you can deliver higher peak power, okay, and you do not operate at high average power, because that is what your diode cannot really handle, okay. And there is another interesting thing, is that this power can be up to 4 or 5 times the possible maximum power for LEDs shining continuously. This scale up really is a reason of using this pulse width modulation. At the same time, the transmission part does not carry the DC component, and so the receiver can continuously adapt itself to the surrounding illumination and detects changes only, because if you are using that, so pulse essentially means change in the with respect to a ambient and the surrounding illumination and the noise, okay. So, it is not a continuous transmission, so you can detect the changes, and that is precisely the reason why this pulse width is used. And what we say that integrated IRDA transceivers do have filters that eliminate noise other than the IRDA frequency range, okay. So, other noise is eliminated. So, this detection becomes important and critical in view of the surrounding illumination as well as the noise sources. And in fact, if you have used such a link for transferring the data, you will find a slight disturbance. In many cases, there are disturbances cause the data interrupt, okay, and in various ways you will find that message coming up, okay. Particularly, it is very sensitive to line of sight, because if it is blocked, then obviously you cannot really have a data transfer. Now, since it is a protocol, so this so far what we have talked about simply how the data is transmitted in terms of the bytes, okay, and it is an asynchronous transmission. So, we have got a start bit and a stop bit to indicate that. So, what we really have is, in this case, a definition of a packet or a packet structure. Packet consists of two start words followed by the target address, okay. IRD devices are assigned numbers by means of IRDA protocol. So, they are able to unambiguously identify themselves. So, this property is similar to that of your USB as well as IEEE 1394, okay, because here also I can just plug in a device, okay, just bring a device near to a receiver and then they can start really communicating with each other. The whole packet or the frame including CRC16 is generated by IRDA compatible chipset. What is the CRC16? This is for doing error detection as well as subsequent error correction. There are a set of protocols which have been defined for this purpose, just like you have got on IEEE 1394 layers of protocols. Here also you have got layers of protocols. First is what is called infrared link access protocol. Although typically it is not like a big network which gets it is set up, it is more like a one-to-one connection in many cases, in majority of the cases one-to-one connection, and the connection gets established when the devices are in vicinity of each other, okay, because you have to have them in the line of sight, but still then you need to have this proper protocol to ensure there is a correct transfer which takes place. So, you have got infrared link access protocol, which encapsulates the frames, provides arbitration, because there has to be only one primary device and others are secondary, and communication is always half to play, okay. Both the sides really does not communicate, and this protocol describes how devices establish connection, close it, and how are they going to be internally numbered, because until and unless they are internally numbered they cannot be accessed, okay. Even if there are multiple devices and if I have to access them, they got to have a unique number. And what is interesting to note is that although we are not telling, and it is not a host based kind of a protocol, but there is typically always one primary device and others are secondary. On top of this, you have got infrared link management protocol. So, every device lets know others about itself via this IR-LMP protocol which runs above IR-LAP, okay. So, LMP's goal is to detect presence of devices offering a service, to check data flow, and to act as a multiplexer for configurations with more devices with different capabilities involved, okay. If there are not more devices, then really this multiplexing capability is not really of significance, okay. So, applications use this layer to find out if a required device is within a range or not. So, typically if you are using a PC with your infrared support, you will find the moment you get a device inside this vicinity, the PC starts responding, it says that there is a infrared recipient in its vicinity, okay. So, an application when it is running or managing an infrared port typically uses this protocol to figure out whether there is any device with which it can establish a connection. Then you have got transport protocols, okay, which is IRDA transport protocol, which is called also tiny TP, because transport protocol is essentially to maintain these virtual channels, that is point to point connections. It performs error corrections if there are packets lost, how the packet loss has to be taken care of. Then it divides data into packets, reassembles original data from packets, and if you are familiar with the concept of networking, this is exactly the functionality which is associated with the transport layer of any network. On top of this, you have got a object exchange protocol, okay. So, these actually have got the a kind of transactions which are defined over here. Say defines put and get commands, okay, thus allowing binary data transfer between the devices, okay. So, actual data transfer which takes place between the devices, that goes through your put and get. In fact, when you find out on a PC, if you are doing this transfer, that whether this data to be accepted or received or sent, that gets translated into effectively this put get commands. The standard defines what a packet must contain in order for the device to recognize each other and communicate. In fact, these layers of protocols that I have defined, this basically defines a generic kind of data exchange. Now, what is interesting, you will find that in order to make devices exploit this protocol effectively, there are also application level protocols defined. Okay. So, there are extensions for defining what is called extensions to IROBX for IR mobile communications. So, these are extensions for mobile devices like handhelds, PDA, cellular phones, and they defines how to transfer informations typically pertaining to GSM network, okay? Address books, SMS, calendar, dialing control, digital voice transfer over IR, etc. Okay? So, you are actually having a GSM device, it has got its GSM capability, but you are providing the interface for that GSM functionalities through IR link. And so, you define protocols specifically for these kind of applications. Then you say infrared transfer picture, this is another protocol, how to transfer pictures over infrared interface. So, what I wanted to show here through this, I am not going into any of the details of these protocols, that depending on the application, you have got the application layer mechanisms which have been specified over these kind of interfacing, generic interfacing specifications. Obviously, these are not full-fledged computer networks, okay? But what you can realize is many of the networking related concepts have been flown in and have been used to specify the protocols, simply because that makes the management of multiple devices more efficient and ensures that data transfer is robust and you can handle errors in a better fashion. This is a kind of an application scenario which people conceive of, and it is being used in the context of embedded systems. So, what you see that all these are embedded systems. In fact, other than this PC, all these are embedded systems. This can be a digital diary, okay, which is again an embedded system, which may have an IR link to a pager. Okay. This pager can have a IR link to the PC to load your phone book, calendar, etc. Now, here you have got a handset, a mobile, and mobile can communicate with any of these devices. Okay. This is a mobile to mobile communication. Okay. A link which we are showing here, it is a mobile to mobile communication with a IR link. And then you can have a car cradle, okay, and this is a voice call control. That means you can have a mobile kept there, okay, you are not really using your hand to control the mobile. You can have a voice interface to the mobile, okay, and the whole voice interface could be through an infrared link, okay, through an wireless link. So, you just speak out to a microphone, okay, through an wireless link, it can be connected and delivered there, okay. So, the whole point is, if you look into it, this is some kind of a personal network. It's, although it's not truly a personal network, or technically what today is being defined as personal network, but you can see that what you can establish through this kind of an IRDA protocol is a lots of functional utilities which are required for individual operations that can be networked. Typically, we talk about networking of computers. This is an example of networking of appliances. The other option of this kind of a communication or networking devices together is using protocols in radio frequency. we had looked at till infrared at radio frequency. So, here the electromagnetic wave frequencies in radio spectrum is what is used. Obviously, you would require the analog circuitry and antenna needed on both sides of transmission. The advantage here is the line of sight not needed and transmitter power determines the range. Okay. Now, we shall not go into more details of these wireless communication links and how to have a complete full-fledged network built around wireless communication link. This we shall discuss when we shall be discussing embedded systems with full-fledged networking capability. In that context, I shall pick up these protocols. But this is also another way of getting embedded systems communicating with each other. But there are some generic issues which, since we are finishing off this bus structure and interfacing protocols, I would like to touch upon. One very basic issue is error detection and control. Okay. In fact, you will find that almost all these protocols, they have got error detection and correction capabilities built in as part of the lower layers. So, that is a part of bus protocol. So, what is error detection? Ability of the receiver to detect errors during transmission. Error correction, ability of receiver and transmitter cooperate to correct problem. So, it is typically done by acknowledgement or retransmission protocol. But when you are doing an isochronous transfer, you really do not have a provision for retransmission. So, there has to be some kind of a post processing to take care of that errors. What kind of errors can occur? The simplest error is bit errors. Okay. So, here the single bit is effectively inverted. So, when we try to detect a single bit error, we can detect a single bit errors, but not all burst bit errors can be always detected. So, what is a burst bit error? Consecutive bits received incorrectly. Okay. Now, if we are using typically a data level tools, and we use data level tools to check whether we have correctly received the bits or not. So, a most common mechanism is parity. An extra bit is sent with word used for error detection. If there is an isolated error, we can detect it. If there is always an even number, so it get masked, I cannot detect that error if I am using a parity. So, it can be an odd parity or an even parity which is used. And in fact, this is a basic error detection scheme which is there in as part of any of these asynchronous protocols, even as simple as that of RS-232C protocol. Checksum, now checksum can be generated using variety of algorithms, is an extra word sent with data packet of multiple words. So, that word really indicates whether the data packet that you have received is correct or not. So, that means a receiver, it uses the data part of the packet to recalculate the checksum and matches with the checksum byte which has been transmitted. If the two matches, it ensures the data has been received correctly. Okay. So, a simple example of a checksum is an extra word which contains XOR sum of all data words in the packet. Obviously, we cannot use a very complex checksum because that also puts a load on the interface circuitry for the purpose of verification. And what are the current trends? See, we have seen that when we looked at the interfacing protocols, primarily they have in fact serial interfacing, it has moved into a kind of a switched network. Okay. In fact, packet switching is what is typically the trend. In fact, today you have bus structures. Okay. When we refer to bus structures, we are referring to how the CPU is to be connected to peripherals in the memory. There also the trend is towards designing high speed switched serial interconnects. That means effectively bringing in packet switching over there. Okay. So, use of packet switching for improving what we call transfer efficiency. And in fact, we had discussed, if you remember, we had discussed the basic concept of split transaction. That means you carry out a transaction, and if my slave is not currently able to do it, the transaction, it remembers the identity of the master and later on carries out the transaction. this is the basic concept and very similar to that of your packet switching. In fact, PCI Express, which is a current standard which is moving into the PC, okay, PC scenario, and soon will move into embedded systems, and there are other standards moving into embedded systems, where the basic trend is to go into high speed packet switching serial interconnect for connecting the peripherals and even the memory. Okay. And in fact, the bus structure or these bus structure protocols becomes a very key issue, because you can design fast processors, you can design fast memory, but everything will go to vain if you do not have a proper bus protocol and high speed connection. And that is why this is a very important issue for design and development. So, this brings us to the end of this topic as such. So, what we have studied is bus structures used for connecting CPU and peripherals. We have also looked at interface specifications for connecting two or more embedded systems. We shall switch to some other topic in the next class. In particular, we shall look at how to manage power in an embedded system in the next class. Any questions?
So, the personal network that you have shown, in the personal network that you have shown, every device is moving. How can we ensure the line of sync?
Yeah, what you are telling is, in case of an IRD application, if every device is moving, I cannot do it. Absolutely true. Okay? But the whole idea is that when they are in the line of sight, I can use them. So, it is not like a network connection with a kind of a persistent computation, just like you look at in an ordinary network that computers are connected over the network and you continuously do a job. It is not like that. It is connected when it is needed. So, connection on need. So, I shall connect my device, okay, in line of sight when I need it, when I need to load my phone book or my diary. Later on it is not needed. So, I can move around. Okay.